Okay, so I will continue talking about the limits. Okay, so there are several other definitions that we will need to consider. So the first one is what does it mean for the limit as x approaches plus infinity of f of x equals some L. Then this means it has a horizontal asymptote, or let's say we have this graph. Okay, or just let's say we have this graph. Okay, so when x approaches infinity, you can see that the value will approach this value L. So what it means, because here x approaches infinity instead of approach a point, so we don't have this some point A, but this becomes infinity, which means when x is very large, then f of x will be very close to L. Okay, so as x approaches plus infinity, f of x will approach L. But how close? Then do a similar thing. You look at the epsilon neighborhood of L, which is the interval from L minus epsilon to L plus epsilon. And then you want all the large enough x to have the value within this interval. So what it means for large enough is that you can find some number n bigger than 0, such that for all x bigger than n, its value are in this interval. Okay, so here, so it's clear that we should define this way. This is true if and only if for all epsilon bigger than 0, we can find some n bigger than 0, such that for all x in R, let me just say for x, no, for x in R, if x is bigger than n, then f of x will be close enough to L. So the absolute value of the difference will be less than epsilon. Okay, so this is what it means for the limit at plus infinity. And similarly, we can define the limit as x approaches negative infinity of f of x equals L. Then this means for some for some negative value, like for some negative n, right? We can find some negative n. I mean, for every epsilon bigger than 0, we can find some n bigger than 0, such that for all x less than negative n. Okay, so here n is also positive, but we choose negative n to be the point. So then when x is less than negative n, then all the values will be within this interval. So then this is for all epsilon bigger than 0, we can find some n bigger than 0, such that for all x in R, if x is small enough, okay, if x is less than n, then the absolute value of f of x minus L would be less than epsilon. And then we can also define the case when the limit equals plus infinity or minus infinity. So we first look at the case when the limit as x approaches a of f of x equals plus infinity. So what it means is that when x approaches a from either the right or the left, then the function will go to infinity. Okay, so it will have a vertical asymptote like this. So what it means for close to plus infinity or approaches plus infinity is that for all large, I mean, this means when x is close enough to a, f of x is very, very big. So it can be arbitrarily big, or it goes to plus infinity. But then what is like the neighborhood of plus infinity? It is the set of all numbers such that it is bigger than m. Okay, so you can think of the interval from m to infinity as a neighborhood of plus infinity. Okay, so what it means for a function to go to infinity is that for each big enough m bigger than 0, if we look at the graph that is above m, then you can find some open neighborhood around a excluding the point A, such that for all value in this interval, the values, for x in this interval, all the values are bigger than m. Okay, so if we write it down, this is for all m bigger than 0. So this m means like a large number. Okay, that is positive. We can always find some delta bigger than 0, such that for all x in R. So here x is close enough to a. So if the difference from x to a is bigger than 0 and less than delta, then f of x is very big. It is bigger than m. So f of x can be arbitrarily big if x is very, very close to a. So similarly, we can also define the limit when it's negative infinity as x approaches some point. So this means at a, we still have the vertical asymptote, but both sides will go to negative infinity. So what it means is that still for m bigger than 0, then this will become negative m, okay? Then all the points that are close enough to a will have the value that are less than negative m, okay? So if we want to write it down, this is for all m bigger than 0, okay? So when m is very, very large and positive, this means minus m is very, very small and negative. So for all m bigger than 0, we can find some delta bigger than 0, such that for all x in R, if x is close enough to close enough to a, but not equal to a, then f of x will be very, very small. But how small? Less than negative m. Okay? So this is the definition of when the limit is negative infinity. And now we can also define, if you wish, the limit x as x approaches, for example, plus infinity of f of x to be plus infinity. That means when x is very, very large, then the f of x is also very, very large. So similarly, if this is plus infinity, then we use some m bigger than 0. Then it will be arbitrarily large. But then here x is also very large. So then we can find also, so here we can find, so for any m bigger than 0, we can find some n bigger than 0, such that for x bigger than n, f of x is bigger than m, okay? So for x, we find some n that is large, such that for x larger than n, f of x is bigger than this m, where m is an arbitrary positive fixed number. So this means for all m bigger than 0, we can find some n bigger than 0, such that for all x in R, if x is bigger than n, then f of x is bigger than m. So similarly, you can define, for example, this becomes negative infinity, this becomes negative infinity. I will show you that example, okay? And also you can define, for example, x when x approaches infinity, the limit is negative infinity. But I will show you the example when both are negative infinity. And you can figure out all the other two cases. So this will be true if for all m bigger than 0, if you look at negative m, then you can find some n bigger than 0, such that for all x less than negative n, then all the values are less than negative m, right? We use m and n to be positive just to make things easier, because we want to evaluate some inequalities. And if we have some negative numbers, then we have to change the sign, and we don't want that to happen. So usually we'll just choose the positive number m and n, okay? So this is equivalent to for all m bigger than 0, we can find some n bigger than 0, such that for x in R, if x is less than negative n, this means x is very, very small, smaller than some very, very small negative number, then f of x is very small. It is less than negative m for an arbitrary m. Okay. And then I need to talk about the one-sided limits. So we define, for example, here, in this case, if this is 1, this is 2, and this is 3, and this function is f of x, then you can see in this case f of 2 is equal to 3. And the limit as x approaches this point, sorry, I will call this point a, okay? So f of a is equal to 3. And the limit as x approaches a from the right, okay? We will denote by a plus of f of x would be the limit as x approaches a from the right. Then we look at the graph. It clearly approaches 2. And if we look at the limit as x approaches a from the left, then it appears that it will approach to 1. Okay? So these two limits are called one-sided limit. One is called the right limit, and the other is called the left limit. So what's the definition? Well, to define, for example, the right limit, all we need to care is the interval from a to a plus delta for some delta bigger than 0. So everything else is the same. So like, for example, when we define the right limit is equal to 2, then for every epsilon bigger than 0, we can find some delta bigger than 0, such that for all x on the right part of this deleted neighborhood. So we only look at the right to the a, so which is from a to a plus delta. We want this to be true, that f of x is the distance from f of x to 2 is less than epsilon. Okay, so in general, the right limit at a of f of x is equal to L if and only if for all epsilon bigger than 0 we can find some delta bigger than 0, such that for all x in R, if x minus a is bigger than 0 and less than delta. Okay, so without absolute value, this means this is positive. So this will imply that f of x is close enough to L. So here it's the same. And then if it's the left, if we change it into the left limit, then here we just change it into either a minus x is bigger than 0 less than delta, or we just say x minus a is bigger than negative delta and less than 0. You can check that they're equivalent. Okay, either one of them, and then imply the same thing. And if you think it's too complicated, then you can probably just say in the right limit it's x in a plus delta, and in the left limit it's x in the left part, which is a minus delta and a. Okay? So this is the left limit, and then this is the right limit. Okay? And then you can see clearly that a function has a limit at a point if and only if both one-sided limits exist and then are equal. Okay? So in general, the limit at a point exists if and only if if and only if the limit at both sides exist and are equal. Okay, so just as the last time, this actually has 3 meanings. The first one is that the right limit exists, and then the left limit exists, and also they are equal. Okay, it's very, very important. Okay, and now I want to talk about some cases when the function is not continuous. Okay, now we have seen many different ways of many different definitions of limits, and in practice, what are the common cases when a function is not continuous at a point? Okay, which means we want to look at some common cases of the discontinuities. So if a function is continuous, then it will be very, very, let's say, smooth, okay? But it doesn't need to be. It can have some corners or cusps, but it will be continuous, right? So if you go from, if you look at all the points close enough to A, then it is connected, right? That's what it means for continuous functions. So geometrically speaking, continuous functions will always look like something like this. But what are the cases when a function is not continuous at a point? So there are many cases, and there might be some overlaps. I'll try to give some examples. So the first case is when the function is not defined at this point, right? So for example, even if both limit exist and are equal, the limit does not exist. The value does not exist. So if f of a does not exist, so or it means that f of a is not defined, or it's not defined, then it cannot be continuous, because if it's continuous, then the value must exist and is equal to the limit. Okay, so the first case is when the value does not exist. The second case is that, for example, the limit exists and it is defined, but it's defined somewhere else. So this is the case when the limit at a exists but not equal to the value at a. Okay, so even if the value is defined, and even if the limit exists, it doesn't need to be continuous. For example, this is not continuous. Okay, so case 3, this is when both one-sided limit exists and the value exists, but not not all of them are equal. So things like this. Or for example, it is right continuous in the sense that the right limit is equal to the value. So this is right continuous, but not left continuous because the value is not equal to the left limit. Okay, so this is only right continuous but not left continuous. And although you don't need to really know this definition, but so here so this is what it means. So in this case, the left limit is not equal to the right limit. So in this case, you don't actually care what the value is, because if this is true, then this means the limit at this point does not exist. Okay, because the left limit is not equal to the right limit, so the limit at this point does not exist. So then it cannot be continuous at this point. Are there any other examples? Yes. For example, here, if the limit is infinity, like in this case, at least for one of them, okay? So if one of the one-sided limit approaches infinity, then it cannot be continuous. Why? Because if it is continuous, then let's say the value at a is this point, but it approaches infinity, but this point is a finite value. It cannot be infinity, right? We cannot define the value to be infinity, which means in this case, at least one of the one-sided limits, let's say the left limit, is plus or minus infinity. So in this case, it cannot be continuous, whatever the value is. Okay, and definitely if both of them are plus or minus infinity, either this one or this one, then it cannot be continuous. Okay, no matter where you put this value. So in this case, let me just draw this way. And there is actually another case, which is actually very, very important, but it can be very hard for beginners to understand. So this is the example of f of x equals sine of 1 over x. So if you look at the graph, then it's something like this, right? So it will oscillate. It will oscillate from -1 to 1, okay, at around 0. So you can see that, let me sketch and put the x-axis here. So this is the origin. So you can see around this point, so from the left, then it will oscillate from 1 to minus 1, from 1 to minus 1, from minus 1, infinitely many times. So the limit does not exist. So even the one-sided limit does not exist, okay? So the left limit of this function, sine of 1 over x, does not exist. And also clearly the right limit is similar, does not exist. And it does not exist because of a very, very special reason, because it oscillates, okay? Because it oscillates from minus 1 to 1. So this is very special. Okay, so this is also a kind of discontinuity. And these are actually basically all the discontinuities that we will see, at least in calculus. Okay. So this is about discontinuity. Let me randomly sketch a graph, and then we will see what are the points when the function is not discontinuous. Okay, let me randomly sketch a graph. Let me do probably in this way. And this point is, let's say this point is, no, I don't care. I mean, it oscillates at this point. Okay, so what are the discontinuity points? So the first point is here. So we call it A1, right? Because the left limit is not equal to the right limit, so the limit does not exist. And the second one is here, because although the limit exists, the limit is not equal to the value at this point. The third one is A3, because the left limit is negative infinity. And the third one is this. So this is when the function oscillates at this point, which means both limit does not exist. Both one-sided limit does not exist. Do not exist. Okay. So this is about the discontinuities. And in the next video, I want to talk about the squeeze theorem, and also very importantly, I want to talk about the extreme value theorem and also intermediate value theorem. So they are very important, but we will not prove it. We will just know how to state the theorem and how to use them. And after that, we will talk about